Okay, good morning, students. Okay, today we will see one more problem on Brayton cycle, and we are seen in previous lessons. Okay, we are using three different performance increasing methods of the gas turbine. Okay, that is one is gas turbine with intercooling, and second one is gas turbine with reheating, and third one is gas turbine with regeneration. Okay, in the present problem, okay, we will discuss the gas turbine with intercooling method. Okay, the gas turbine with intercooling method. Okay, see the present problem. Okay, we are using the two compressors. See, 1 to 2 isentropic compression and 3 to 4 isentropic compression, and between these two compressors we are arranging one intercooler. Okay, that intercooling process is 2 to 3 process. Okay, we are rejecting the compressed air temperature after compression in the first compressor with the help of a intercooler arrangement. In the intercooler arrangement we are decreasing the temperature of compressed air by using the one heat exchanger, that is intercooler, up to the temperature equal to the T1 temperature. T1 is equal to T3, and after rising the temperature in the second stage compressor, that is T4 dash, and that must be equal to the T2 dash. So this type of intercooler is called perfect intercooler. Perfect intercooler. Okay, this type of intercooler is called perfect intercooler. Okay, we are arranging the perfect intercooler between the two compressors. After compression, second stage compression, the air is heated in the combustion chamber. After that, the hot air with high pressure and temperature introduced in the turbine section. In the turbine section, okay, we are getting the work output. After getting the work output, that work output we are using in our application, that is the turbine work. And this process is followed by isentropic expansion process. PV power gamma is equal constant. Okay, and let us see how do we find the performance parameters in the present problem. Okay, what is the given data? The pressure ratio of an open cycle turbine plant is 5.6. The pressure ratio is given. The pressure ratio is, okay, 1 to 2 process and 3 to 4 process. 1 to 2 process and 3 to 4 process is the pressure, compressed air. Air is compressed in the 1 to 2 process and 3 to 4 process. Okay, we are using that pressure ratio in the 1 to 2 process. In the second stage compression, okay, we will see how to find the pressure ratio of second stage compression. Okay, the first stage compression ratio is P2 by P1, that is given in the given data. P2 by P1 is equal to the 5.6, and P2 is equal to P3, and P4 by P3 we have to evaluate, and from the relation, okay, that relation is P2 by P1 is equal to P4 by P3. Why we are using this relation means, okay, these two stage compression having same quality, same equality work input, that mentioned in the present problem. Two stages receiving the same work input. That's why the pressure ratio is same. P2 is equal to P3. From this relation, we can get the pressure ratio. Okay, P4 by P3 also square root of 5.6, that is equal to the 2.366. The second compression pressure ratio is 2.366. Okay, next we have to find the unknown temperature in the cycle. What is the given in the present problem? What temperatures is given? Okay, T3 is given, maximum cycle temperature, that is equal to the T5. Sorry, T5 is given. T5 is equal to, that is maximum temperature, limited temperature, that is 700 plus 273 Kelvin. T5 is given, and what else is given? T1 also given in the present problem. Okay, that is air is taken at 30 degrees centigrade, and P1 is 1 bar. 30 degrees centigrade. T1 is equal to 30 degrees centigrade temperature. Okay, we have to convert it into kelvins. 30 plus 273 kelvins. Okay. Next we have to find the unknown temperatures, that is T2 and T4. Okay, T2 by T1. T2 by T1 is equal to P2 by P1 whole power gamma minus 1 by gamma. Okay, the pressure ratio is given. P2 by P1 is given, that is 5.6, and T1 is given, that is 30 plus 273. Okay, 303 Kelvin. Okay, T2 by 303 Kelvin is equal to 5.6 whole power. Okay, gamma value for turbine and compressor is same in the present problem. 1.4 minus 1 divided by 1.4. From this we can easily calculate T2 value. Okay, that T2 value is equal to the 404.44, sorry, 389.23 Kelvin. 389.23 Kelvin. Okay, later we have to calculate the T2 dash. That T2 dash is the actual temperature rise in the first stage compression. Okay, we have the efficiency of the compressor, that is 85% in the present problem, that is 85%. Okay, so the compressor efficiency is equal to T2 minus T1 divided by T2 dash minus T1. In this relation, we have to calculate the T2 dash. Compressor efficiency is equal to 85% and T2 value is equal to 389.2 minus T1 is equal to the 303 Kelvin, and T2 dash we have to evaluate in this present problem, that is T2 dash is equal to, in this relation only unknown value is T2 dash, that T2 dash is equal to the 404.44. 404.44. This value you can also see in your calculators. T2 dash is equal to 404.44 Kelvin. Later we have to calculate the compressor work input. Okay, the compressor work input is equal to MCP into T2 dash minus T1. MCP into T2 dash minus T1, that is the first stage compression work. Okay, M value is given in the given data, that is 1.2 kilogram per second. 1.2 into CP value is given in the given data, that is 1.02 into T2 dash is 404.44 minus T1 is 303. In this relation, the compressor work is equal to, if you calculate that compressor work, the compressor work is equal to the 248.32 kilojoule per second, that is kilowatt. Okay, this first stage compression work is equal to the second stage compressor work also. WC1 is equal to the WC2. First stage compression is equal to the second stage compression also. First stage compression is equal to the second stage compression also. Okay, later we have to calculate the temperatures in the turbine process also. Okay, up to now we completed the finding terms of T2 and T2 dash. We have to evaluate the unknown temperatures, that is T4 and T5 we have to calculate. Okay, we have the pressure ratio P5 by P4. P5 and P4, P5 is equal to P4, we know the relation, and T5 by T6, turbine expansion, T5 by T6 is equal to P5 by P6, P5 divided by P6. Okay, whole power gamma minus 1 by gamma. Okay, in this relation the unknown value is T5 by T6 is known value, gamma minus 1 by gamma. Already we determined P4 by P3. P4 is equal to P5 and P3 is equal to 2.366. Sorry, uh, 5.6 whole power gamma minus 1 by gamma. Okay, T5 divided by T6 is equal to the 5.6 whole power 1.4 minus 1 divided by 1.4. Okay, in this relation, T6 we have to calculate, and T5 and T6 both are unknown values, and T5 is given in the given data, that is 700 plus 273. Maximum temperature in the cycle is T5, that is given in the given data 700 degrees centigrade. Okay, that 700 degrees centigrade you have to substitute in the T5 place. 700 plus 273 divided by T6 is equal to the 5.6 whole power 0.4 divided by 1.4. Okay, so T6 is equal to, okay, T6 is equal to 589.7 Kelvin. After calculating the T6, we have to evaluate the T6 dash. The turbine efficiency is equal expansion process is T5 and T6. T5 minus T6 dash divided by T5 minus T6. Okay, in this relation we have to calculate the T6 dash. Okay, turbine efficiency is equal to 90% is given in the given data. Okay, 90 is equal to T5 is equal to 70 plus 273, that is 973 minus T6 dash, okay, divided by 973 minus T6. Okay, what is the T6 value? 589.9, 589.7. Okay, from this T6 dash is equal T6 dash is equal to the 623 Kelvin. 623 Kelvin. After calculating the T6 dash, we can easily evaluate the turbine work. Okay, W turbine is equal to the MCP into T5 minus T6 dash. T5 minus T6 dash. T5 is 973, T6 dash is 623. We can substitute M value is equal to 1.2 and CP value is equal to 1.02. Then turbine work is equal to the 422.28. 422.28 kilojoule per second, that is kilowatt. Later compressor work, two stage compressor work, that means we have to multiply the compressor work with 2. So MCP into T2 dash minus T1. T2 dash minus T1. T2 dash value already we determined, that is 404.44, and T1 is equal to the 303 Kelvin. So the compressor work will be equal to 173.96. Sorry, 422.28. Compressor work already we determined, I think here 248.32 into 2 into 248.3. 2 into 248.3. Okay, later we have to calculate the net work output. Net work done is equal to the turbine work minus compressor work. After calculating the turbine work, after calculating the compressor work, you can easily substitute the turbine work and compressor work. Okay, you can easily evaluate the net work done, that is equal to the 173.96 kilojoule per second. Kilojoule per second, that is equal to the kilowatt. And efficiency of the plant also we have to determine in this problem, that is equal to the net work done by heat supplied. Heat supplied is equal to the mcp into here we supplied heat from T5 to T4 dash, T5 to T4 dash. Okay, that is we have to calculate T5 minus T4 dash. T5 minus T4 dash, that is equal to, if you substitute T5 and T4 dash, you can get 695.92 kilowatts. After calculating the QS, you can easily calculate the plant efficiency by use of these two terms, 173.96 divided by 695.92. Okay, the efficiency of the plant will be 25%. Okay, I will repeat again, please listen. Okay, in the present problem belongs to gas turbine with intercooling method. Okay, in the gas turbine with intercooling method, we are arranging the two compressors. That compressor works are 1 to 2 and 3 to 4. Okay, that is ideal case. Okay, in case of theoretical one, 1 to 2 dash and 3 to 4 dash. Okay, theoretical one means in the present problem, we will observe the efficiency of the compressors. In the present problem, the efficiency of the compressor is 85%. Okay, two stages having the same work done. Okay, that is equal to the 248.32 kilowatts. Okay, 248.32 kilowatt. Two compressors having the same work input means no need to multiply the compressor work with 2. Okay, this one is the compressor work. 248.2 is the compressor work. So we have to calculate the unknown temperatures, that is T2 and T4 and T4 dash by applying the pressure and temperature relations. Okay, with the help of this pressure and temperature relations, we can easily calculate the unknown temperatures in the cycle. Okay, that unknown temperatures are T4 dash and T4 and T5 and T6 dash. After calculating the temperature, we have to evaluate the turbine work, that is mcp into T5 minus T6 dash, and compressor work, that is mcp into T2 dash minus T1. After calculating the turbine work and compressor work, we can easily calculate the net work done and efficiency, plant efficiency. Okay, for calculating the plant efficiency, we need to calculate the heat supplied. Okay, we are supplying the heat from point 4 dash onwards. 4 dash to 5 we are supplying the heat. Okay, later we can easily evaluate the plant efficiency, that is equal to the 25%. Okay, in next class we will see one problem on reheating. Okay, thank you.